Hello there, I'm Gregory Carlson, and we're learning college algebra. We're on the last section of the first half, section 3.6. We're going to finish with something a little easier, direct and inverse variation. So let's talk about them. Direct variation, both of these are ways that variables relate to each other. And so direct variations are two variables together of the form y equals kx, where k is a constant number. Basically, direct variation is a line through the origin. That's really important that it go through the origin. You can see we have no y-intercept here. Inverse variation, on the other hand, is two variables that move of the form y equals k divided by x. So y equals some constant number divided by x. I wonder if there's some graph that looks like that. I know! How about 3.5? We just did hyperbolas. So y equals k over x is a hyperbola, like we did in 3.5, and y equals kx is just a line through the origin. K is the constant of variation, which means that k is always going to be the same for that system. And we're going to be using constants of variation in application problems. You see this in chemistry a lot, and physics, and a lot of other classes that relate to known quantities. By the way, know that this is y varies directly with x. If I said x varies directly with y, the equation is x equals ky. So notice that the equation is a little bit backwards, okay? So if it's y varies directly with x, it's y equals kx. If it's x varies directly with y, it's x equals ky. So whichever letter comes first is the letter that should come first in your equation. And that's the same for inverse too. This is y varying inversely with x. Let's look at a few example problems. This is the last page of notes for the midterm. They tell us x varies directly with y, and x is 35 when y is 5. Find x when y is equal to 13. So this is really easy. Step 1, write your equation. X varies directly with y. So the equation should be x equals ky. Now, we want to know what x is when y is 13, but first we need to figure out what this constant is. And luckily, they told us a complete system. They said x is 35 when y is 5, so we can use that information to figure out k. X is 35 when y is 5, just like that. So let's divide both sides by 5. When we find that k is equal to 35 divided by 5, which is 7. So kind of, that's the key to the problem. We've just unlocked the equation. Because this is a constant number, we can rewrite the equation as x is equal to 7 times y. So you can think of it as we've updated the equation by figuring out what k is. And now that we know that and notice that k is constant. It's always the same. So what is x when y is 13? All you got to do is now replace y with 13 and get the answer. So it's going to be 7 times 13, which is 91. That's the answer. So not too difficult. This process will almost always be the same. First, use a complete system to figure out k, right? Then update your equation, and then you can solve a partial system because you figured out your constant of variation. Let's do example 2. Y varies inversely with x. So let's start with our equation. Y is inversely with x, so that'll be k divided by x. Now here's how I remember these equations. It's always, notice that k is always on top. And you do need a k, so make sure you keep that k in there. Don't miss that on a test or something. So k is always on top, and that way your numbers will work out when you're finding and solving for k. So direct is x equals ky, inverse is y equals k over x. It says y is 3 when x is 12. We can use that information to solve for x. So y is 3 when x is 12. So I get 3 is equal to k divided by 12. So to solve this, multiply both sides by 12. The 12s cancel, and I get k equals 3 times 12, or k equals 36. You could box that if you want, because it's a critical step of solving the problem. So we found our constant of variation. So let's update our equation. Y equals our k, 36, divided by x. So we've updated our equation by replacing our constant of variation. Find y when x is equal to 9. Well, we want to know what y is when x is 9, so we'll just plug that in. And 36 divided by 9 is 4. So there's your answer right there. Let's do the next one. This one's a little bit tougher. G varies directly with r and inversely with the square of p. So the way you'd write that as an equation is G varies directly with r, so r is on top, and inversely with the square of p, so p squared should go on the bottom. Now, what have I left out? You should be able to see that I've left something out. Do you see what it is? That's right, it's our constant of variation. Remember, we always need to slap that k in there. So here's how you would do G varies directly with r and inversely with the square of p in an equation. If G is 4 when r is 64 and p is 4, find G when r is 325 and p is 5. So just like usual, first we're going to solve for this constant of variation. So G is 4 when r is equal to 64, so this is k times 64 over, and p is 4. And so that's how I plugged everything in. Do you see that? K times 64 over 4 squared. So we can solve this for k. So that's going to be 4 is equal to, that's 16 down here. And 64 cancels with 16 and becomes a 4. So I get 4 equals 4k, and it's pretty obvious that the only number k can be is 1. But divide by 4, divide by 4, 4's cancel, and you get k equals 1. So we found our constant of variation, so we can actually eliminate it completely. It's equal to 1, so I can just write G equals R over P squared. There you go. So now find G when R is 325 and P is 5. So we'll plug in those values. And you should put parentheses around these, because if this was negative, then the negative would be squared. So 5 squared is 25, and 325 divided by 25 is going to be 4, 8, 12, plus 1 is 13. So 25 goes into 104 times, so it's 4, 8, 12, and then 1 more. So the answer is G equals 13. Now it's a little easier because K equals 1, but if K was a number, there would just be a number right here, and you just have one more number to calculate. I'm almost done with this. Let's do part 2, where we will do these application problems. See you there in the last section for the first half.